Okay, hello and welcome to my channel. Today we're gonna be talking about the delta function potential. Alright, delta potential. So first I would like to remind you of, a delta function. A delta function is inherently a rectangle that has a width going to 0 and a height going to infinity with an area of 1. And the way you represent it in, well, graphs, it would be something that they draw like this, or like something like a spike, something like that. But today we're gonna take a look at this form for our delta potential. This is called a delta well. So there is a delta spike and a delta well. Today we're going to take a look at the spike, the well, sorry. This is the coefficient that would kind of dictates the um, severity or something like that. So that is your definition of delta potential. Maybe this next part is not important, so I'll just have it like that. Next, you would want to take a look at the unit of this alpha guy, which is energy times length. And here, get that the unit of energy is equal to h bar square over m times length square. And your length is h bar square over m alpha. So you sub it back in, what you get is, E equal to m alpha square over h bar square. And since we would want to consider bound states here, so the energy would of course be less than 0. So this is E bound and this is less than 0. Therefore, your E bound would be a negative thing with a coefficient. And when we consider delta potential, you can see something like, I would make an example from the infinite square well potential. Outside of the infinite square well potential boundary, there is infinite potential, meaning no wave function can exist outside. And with the delta potential, the potential here at x equals 0 is infinity. Therefore, our wave function cannot exist there. So there must be a discontinuity when you talk about a system with a delta potential. So first condition would be, should draw a line here. Well, first things first, your x gotta be different from 0, as I said. Yeah. So now we're gonna write our time independent Schrodinger equation, and I would just like that. So it would be brief psi. We do not consider inside, at x equals 0, therefore it's just like that. And instead of minus k squared, now we're just gonna take a kappa square, and this kappa square is greater than 0 because we're considered the bound state energy. And the bound state energy is of course negative. And negative is equal to positive. So therefore, our solution, acceptable solutions, are the form of exponential functions. So plus minus kappa x. Right, there we go. And you have this, and from the x cannot be equal to 0, we can also say that in this system there are no odd bound state. As you know, like when you have E1, this is the origin, it would be something like this. So it gotta cross at x equals 0, and since x cannot be equal to 0, E1 cannot exist. Therefore, no E1. So no odd bound state. So no E1, meaning that there can only be one bound state, which is the ground state. Only one bound state. Okay, there we go. And our wave function would look something like this. And here, when you take this guy, you have this guy, you take x greater than 0, the term here would explode and go to infinity. The term, look at that, is infinity. And when you take x less than 0, this guy would explode to infinity, or minus infinity. Okay, I don't remember that. You just have to know that when you take either this guy to be less than 0 or that guy to be greater than 0, they're gonna explode. Therefore, your psi would be E minus and E plus. Not really E plus, but yeah. Less and this guy greater than 0. Because if it explodes, and so we wouldn't want that. It explodes, so it would result in a 1 anyway. So that would give you 0 so you wouldn't want that. Yeah. So that would be our wave function right there. Next, we would want to take a look at the differential equation. Let's just erase sun over here. We're going to do this by the default method for delta potential, which is integrate from this point very close to the delta function, and this point very close to the delta function. So I'll call this epsilon. This point would be epsilon, so you would want to integrate your whole Schrodinger equation you just want to integrate your Hamiltonian from minus epsilon to epsilon. So you're gonna integrate your Hamiltonian. That form. And one thing you can see right away, put this guy out, and that guy turn into maybe I should just write the total. Then derivative, but whatever. Okay, so like this plus the thing that you split, which is your v of x dx, and your v of x would be, well, okay, I shouldn't have erased that. This, you can sub that guy in. Okay, I forgot the psi for that. Yeah. And if you remember, as I said in the Dirac delta function video, your delta function is basically a sifting tool for you to pick specific points. And here it picks 0. Since this guy is not 0, that guy is not that relevant. So you can just rewrite this as just your integral of psi. So I would like to make this less messy. Right in this. There we go. Now we're to M. Okay. So from this, what you can do next is that you take the limit of it going to 0. So it would both affect this and this term simultaneously. This term, the delta, would have something to pick, and somewhere I can fully expand it so you can see it more clearly. Okay, so what did I say? Right now we're gonna take x and let that go to 0. That is taking the limit. So we would get the limit of epsilon going to 0 of these guys. That is epsilon. And as I said, your delta would have something to pick on now. So that is minus alpha at psi 0. That is there. It's like that. Okay, that's, I should write the equal to 0 down here. Okay, so you have this, and there is actually something I forgot to mention, is that the integral of Hamiltonian is also equal to your E integral of from your integral of your psi dx from minus epsilon to epsilon. So from here you get that we're gonna call this guy the discontinuity at 0, right, as delta 0. So we get that, okay, the discontinuity is actually just, yeah, that, right, delta 0 of that is equal to minus 2ma squared over h bar square of psi at 0. That is something you can derive on your own. It's pretty easy to derive, and we're going to use this a bunch of time to get the discontinuity at points. When you deal with, example, a bunch of delta potential in a single system, find somewhere running out of space. This, right, and now, okay, maybe I shouldn't have erased that, but I hope that you remember what wave functions are, as we're gonna apply this guy to our wave function. So this is minus kappa alpha e minus kappa x, and the other term is actually the minus term, which is this. So the term that I was going to write here is this, but I would like to write it as kappa as this instead, so that you can do the grouping. What? Okay, there we go. This is what you have right here. Now we're gonna take it 0. At 0, this guy is gone. This guy is gone. You get 2 minus 2 kappa equal to 2m alpha square over h bar square. It's like 0. Alright. This where we're almost done right now. Now you isolate the kappa and you find the energy, your bound energy. Now this guy is m alpha over h bar. And now you would get your energy, which is E bound h bar square k square 2m. Okay, no, this guy's h bar square, sorry. Get that this guy is minus 1/2 m alpha square h bar square. So that is the same as what we have before, which is a minus a number times m alpha square over h bar square. We get exactly that, and your n is 1/2. All right, so that's it for the delta potential. There is nothing much to talk about, as it is probably one of the easiest system you can solve right now. So I guess that's it for today. Goodbye.